Hello friends! A few weeks ago I made a video in which I took on the task of bringing a whole number of older cordless tools back into use. One of the ideas presented was to modify power tools that were made for nickel-cadmium batteries, especially with strange and outdated form factors, so that they could be used again, but now with more modern 18-volt lithium-ion battery packs. And since we just happen to have a number of Makita brand tools at our shop, I decided to convert these tools of various manufacturers all to the Makita 18 volts standard. But that aforementioned video was a part of my video series on scrapyard repairs. This video though is supposed to be directed at people who are more specifically looking for ideas regarding cordless tools in general. In this video I will present a number of ideas revolving around that topic, and we will start by applying the idea from my earlier video to a few more machines in my possession. Here are just some examples. This red no-name cordless drill was made for 18 volt NiCd batteries and could just as well run on 18 volt lithium ion, if the batteries would fit, that is. This Bosch brand 14.4 volt cordless drill was made in 1999 and the original batteries are dead. I think that it will be able to handle 18 volts though as well. This battery-powered hammer drill is rated at 20.4 volts. Built in 2001, it was also made for nickel-cadmium technology. It's another scrapyard find, but I'm pretty sure it works, it just needs new batteries. Since it's really a high-quality machine, we're going to start by converting the Bosch drill, and here's how I do that. I recently found these adapters here online. They are basically just connectors that fit 18 volt Makita batteries. You can buy them online for just a few bucks, and I will put some links down in the video description. And here is how I convert my tools. The Bosch drill will be our first patient. It was made in Switzerland some 22 years ago, but still looks great. It was sent to me by a viewer, and thank you for that, man. First, one half of the enclosure is opened. In this case, I'm removing these screws with another tool that I already converted in the past. Now that we can look inside, we can see the original contacts that are supposed to connect to the old battery pack. These contacts are a little long though, and that's why I'm shortening them first. And now the two wires of the connector can simply be soldered to those brass contacts. When you do this, you have to know the correct polarity, or otherwise the speed controller of the drill will not work or could be damaged. And now we can already put the enclosure back together. All that remains to be done is to connect the adapter to the enclosure, and in this case I'm using MS polymer adhesive for that. In my other video I also showed an example where I used tiny bolts to fasten the adapter to the drill. And while that polymer is drying, we can do the same thing with that orange hammer drill. In this case we can cut the old wires leading to the battery contacts and solder them directly to the wires of the connector. Heat shrink is then applied in order to avoid a short circuit between the contacts inside the drill. Again, the enclosure is closed and the connector is glued onto it. A very useful yet simple idea that can be realized without the need for a lot of tools or know-how. One thing led to another, and since I had started to experiment with the Makita battery connectors, I had thought about buying a few additional Makita batteries then as well. I ended up buying some tool sets, and then I sold everything out of those tool sets that I didn't need. With those sets also came some Makita 12-volt batteries, and I wondered if similar connectors exist for those as well. I didn't find exactly what I was looking for, but what I found is actually even better. These little devices here have a powerful LED flashlight and a USB port, for example for charging phones. Plus, they can also be used to charge the battery from a 12-volt power supply. Upon opening the enclosure, we find a lot of circuitry controlling those aforementioned features. The only thing missing are two simple leads to access the battery directly. So I soldered two wires directly to the contacts. I cut a little piece of plastic out of the enclosure to make space for the wires to come out, and then I glue them in place so they can't be ripped out that easily. These little things actually make great power sources for electronics experiments, delivering 12 volts and also 5 volts from the USB port. Getting back to the 18-volt connectors though. Once I had found them online, it didn't take long until I thought about using them to connect several battery packs together. By linking the connectors in series, it is possible to achieve higher output voltages, while the individual batteries can still be charged in the standard charger for 18 volts. Fully charged, the batteries reach around 20 volts, and that makes it very easy to calculate what we will get when we connect several batteries in series. One voltage level that I figured could make sense would be 120 volts. In Germany we have 230 volt outlets in our homes, but in many other countries home appliances are built for voltages roughly between 110 and 120 volts, and that made me think. Most ordinary power tools are powered by universal motors. These motors are called universal because they can theoretically run on both AC and DC, and that's why I started to look online for used 120 volt power tools. They are very rare in Germany, but once you find someone selling used tools for 120 volts, you can usually get them for a very low price because almost no one here has a use for them. And one of the tools I purchased is this 120 volt Bosch Drill. It was made by Scintilla, which is a subsidiary of the Bosch Corporation, and including that grey crest drill I keep using in this video, this is the third Swiss-made tool in this episode. So once again I send warm greetings down to our neighbors in the south. Now I mentioned that universal motors can run on AC and on DC, but the speed controllers in these machines cannot. They are triac based phase angle control circuits, in German Phasenanschnittssteuerung, and that is the reason why I have to remove the speed controller that is built into the handle here for a moment. I will show later in the video how a DC speed controller can be built from scratch. For now, I simply want to demonstrate that this power drill can run on 6 18-volt lithium-ion batteries that were connected in series. So that obviously works in principle. But why would you want to power this really rather heavy power drill with batteries when ever more capable cordless drills come out all the time and they only need one 18-volt battery? Well, maybe not a power drill. But what about another kind of heavy power tool? Well, here's an everyday situation that you can certainly relate to. Say there is an existential threat, I don't know, aliens or Soviet agents invaded your town. Now you jump in your car and get the heck out of Dodge. You want to drive into the woods to go into hiding for a while, when all of a sudden you are stopped in your tracks because a steel barrier is blocking the way. Well, I have just the thing. A heavy 120 volt angle grinder powered by a bunch of batteries. So this is a big Hitachi grinder rated at a maximum power of 1700 watts. We will connect it to those batteries in just a minute, but before we do that, there is one precaution I wanted to talk about. Both universal motors and brushed DC motors have a high starting current, meaning when you turn them on, the electric current flowing initially can be much higher than the average current that the motor requires to run at the rated power during normal operation. Many big angle grinders have therefore a built-in current limiting circuit that often simply consists of a power resistor and a two-stage switch, if you will. We have seen that in the past while repairing this Bosch and that Hilti angle grinder. And it works simply like this. A power resistor is connected in series to the motor, limiting the starting current. By pushing that two-stage switch all the way through though, that resistor is then basically short-circuited after a short moment. In many angle grinders, this simple circuit is integrated into the handle. And I don't know if the Hitachi machine has it because I haven't looked inside yet, and just in case you have a machine that doesn't have that as well, here's how I improvised a starting current limiter for this experiment. 10 140 ohm power resistors were connected in parallel, and then there's a switch that I will simply flip once the motor has spun up. It's just a precaution because I don't yet know what the batteries can really handle, and I don't want to break them right away. So as you can see, this does work. However, it would still be nice if we had an actual speed controller and electronic means to provide soft start. One reason is that you need really bulky switches to handle high current DC loads. That is because the arcing in the switch is more severe than with AC, and the wear on mechanical contacts will be much higher. So that is why I built two electronic circuits that can provide speed control and soft start. I will explain how the circuits work later in this video, once we have tested everything. The first circuit is Arduino based, the second one is an analog circuit. This first test setup here is based on an Arduino Uno that is generating a variable pulse width modulation, feeding into a number of MOSFETs driven by a gate driver. And here's how it performs. By simply turning a potentiometer, you can manually speed up the grinder and adjust the speed. Working with microcontrollers has many advantages because you can adjust how the circuit works without having to change the physical layout of the circuit all the time while you're developing it. However, I'm also a big fan of analog solutions and using a number of general purpose ICs if possible. The second circuit reuses most of the power stage of the first one, but this time a TL494 is used as a PWM generator. This circuit allows for pretty much the same basic functionality. A more detailed discussion of the circuits will follow in a few minutes. Okay, so we know that the batteries can power the angle grinder and we also have the electronic means to connect both of these components together. But the setup also needs to be portable and more practical to be of any use. And that is why I already mounted the battery holders on this very piece of wood. It will slide into a wooden shell that will be inserted into this backpack here. This backpack is a new old stock item and was made for the NVA, that's the National People's Army, which were the East German forces during the time of the Warsaw Pact. There are still large stocks in existence and I'm thinking about reuses for them all the time, but more about that later. The wooden box is glued together and hopefully fits right into that bag. padding is also added to make this contraption more comfortable to wear. And I'd say it's time for a field test then. But I said I would also explain the circuits that I built, so let's do that. We start with our load, the universal motor of the power tool. The two inductors are the field coils of the universal motor, and the dotted line is supposed to show that these components are integrated into one component. Power MOSFETs can then be used to switch that motor on and off, and because I didn't have a high voltage, high current MOSFET on hand at first, I connected 3 MOSFETs in parallel. I later changed that to one bulkier MOSFET after new parts had arrived. And while we still are in the power stage of the circuit, it is important to add a flyback diode across the motor in order to protect the MOSFETs. I first used 2 universal type diodes rated at 1000 volts and 1 amp continuous current, but that turned out to be unsuited. And I later added a much faster, much more rugged diode. And you will see that in the last sheet representing the final stage in the design process so far. The MOSFETs are then driven by a gate driver by international rectifier. It's the IR2121 to be more precise. This IC doesn't require a lot of external circuitry to work. The gate driver's input pin must then be connected to some kind of pulse width modulation generator. I first used an Arduino here, and depending on how you program the Arduino, you can use it both for speed control, soft start, or any other number of functions. However, I ended up using an analog solution with the TL494, which is actually a control circuit designed for switch mode power supplies. You can find it in many older computer power supplies or buy it for a few cents, and it's one of my favorite ICs for this type of application. The TL494 needs a low voltage power supply and will accept voltages between 7 and 42 volts for that. You can just derive that from one of the 18 volt lithium ion batteries, for example. The power consumption is absolutely minimal compared to the angle grinder, of course. It's then connected to the common ground, and its 2 output transistors can then be connected in parallel if you want, and they will provide a signal to the gate driver via that voltage divider. The way it is designed, it will make sure to pull the gate driver down when there is no signal. That is important if you don't want the angle grinder to just go off by accident. Next, a timing capacitor and resistor are connected. They comprise an RC circuit that will provide the TL494 with a time constant that will determine the frequency of the pulse width modulation. By inserting a trim pod, you can adjust that frequency. Now the TL494 can oscillate roughly between a few hundred hertz and 500 kilohertz. With this setup, you can adjust the frequency between around 500 hertz and 2 kilohertz. Depending on your application, you must find out which frequency will work best for you. Next, the TL494 has an external voltage reference provided on this pin here. The voltage reference is normally needed so that a switching controller can keep the output voltage of the circuit stable, independent of line and load conditions. Here we simply use it to set other functions of the TL494. For example, these 2 error amplifiers here are connected directly to ground and to the reference voltage via a 56k ohm resistor, so that the TL494 will generate a PWM with the maximum possible duty cycle. By then connecting the OC pin to ground, that maximum duty cycle will be set to around 95%. By pulling it up to the reference voltage, on the other hand, you would limit that duty cycle to under 50%. That feature is needed to use the TL494 for the different topologies of switching converters there are. For a buck converter, for example, values over 50% can make sense, while a push-pull converter will require duty cycles under 50%. And then, last but not least, we can use the dead time control pin to adjust the duty cycle like I'm doing here. This is what actually sets the speed for the motor. But in order to accurately set the potentiometer so that you can adjust the speed from 0 to around 95% over the entire range of the potentiometer, you need a voltage divider with at least one additional trim pod, like I did here. If you don't want to build a speed controller but a soft start function with that, you can connect an RC circuit in addition or instead of the voltage divider. The capacitor will be charged and then the duty cycle will rise as the capacitor is charged. However, this final sheet here represents the final stage of what I built in this video. The 3 MOSFETs were replaced by one 400 volts 15 amps MOSFET. So it would be better to have a MOSFET that can handle even more current, of course, but I didn't have one. The simple diodes were replaced by a 15 amps ultra-fast diode on a heatsink. One word of warning though, I only had a few days to build this and it is a work in progress. There's no guarantee that the circuit will work with your equipment without being damaged. Sorry, but switching high voltage, high current stuff with varying load conditions and inductive components is no easy thing to do. But there is one more thing that I wanted to talk about briefly. A few weeks ago I showed you some of those old yet unused Soviet-era bags I had bought and the patches I was planning to design. The patches are now in production and will hopefully be available by August. Bags with patches and just patches by themselves will then be available for you guys. And I will let you know once we are there. And of course, as always, I'd like to ask you to give the video a thumbs up if you enjoyed it, to let me know that you might want to see more of that in the future. And as always, if you want to help out more actively, you can donate via PayPal, links in the video description, or become a supporter on Patreon under patreon.com/tpai. See you soon, guys.